Section 18.8, the electric field inside a conductor, shielding. So if you're at equilibrium under electrostatic conditions where things have settled into place, right? Any excess charge is going to reside on the surface of a conductor. So if you have a solid metal sphere, that means that all of the negative charges we place on the metal sphere are going to want to get out of the middle and get to the outer edges. This is something we touched on in the earlier videos when we discussed that the negative charges or the positive charges, whatever they are, they're repelled by the others. They want to get as far away as possible. That's going to be on the surface. That's literally as far away as they can possibly be. Because of that, if you're at equilibrium under electrostatic conditions, the electric field is zero at any point within a conducting material. So what's left in the middle here is no charge. So the electric field is just zero. In other words, the conductor is going to shield any charge within it from electric fields created outside the conductor. Let's take a look at how this can play out in an example. So with this idea, if we have a uniform electric field created by a parallel plate capacitor, right, we put a conductor in the middle. Well, in the middle, we're going to draw our electric field lines. Previously, they were just from the positive charge to the negative charge, straight line. Now that we have a conductor in the middle, the positive charges are going to draw negative charges to the left side, and the negative charges will draw positive charges to the right. And so that changes our electric field lines, where we have electric field lines that are going into this cylindrical conductor and then out of the right side. But all of the charges are on the edge here. So in the middle, there's no charge. You could have it just be a gap, an open space, because the electric field is zero when you're inside that cavity. Another note here is the electric field just outside the surface of a conductor is perpendicular to the surface. If you're, again, at equilibrium under electrostatic conditions, which are the cases we're going to be looking at here, that the electric field lines are always going to be going perpendicularly into the conductor. They aren't going to skim the surface. Now, this shielding effect is a rather important one for if you imagine how charges are transferred. And it's one that people have taken advantage of to stay safe, to be shielded from electric charge. So here's one example. Dr. Megavolt created a Tesla coil, which creates great sparks of electric charge, right? And he's in a metal suit. So it's just a bunch of metal pieces welded together, including his helmet is a bird cage, right? And because he's contained within the metal suit, even though he gets, he connects electrically to the Tesla coil and has a huge amount of electric charge flowing, it stays entirely on the surface of the metal suit, of the conductor. And it doesn't go inside, even though the metal is right against his skin, he's perfectly fine. You can check out this video. It's pretty wild to see. This is also why if you're ever driving in a thunder and lightning storm or driving near downed power lines, they tell you to stay inside your car. Because if you're already inside your car, then even if your car gets charged up with electricity, you're going to be insulated from it. Where you get into trouble is when you try and get out of your car, and if you touch your car, now you've created a path for the electricity to flow into you. You are no longer shielded from the electric charges. So that's a neat note here of how conductors don't have an electric field inside them and can produce this shielding effect. So let's look at an example of this. It's a conceptual example to help us understand some of what's going on, and this will feed into the last section that we have. So a conductor in an electric field. A charge is suspended at the center of a hollow, electrically neutral, spherical conductor. What charge is induced on the interior surface of the conductor and then on the exterior surface of the conductor? Right, well, as we're thinking this through, if we have a positive charge in the middle, and we know that we have positive and negative charges in the middle that are free to move about because it's a conductor, what charges are going to want to get close to the positive charge in the middle? It's going to be the negative charges, right? They're going to be drawn towards that positive charge. In response, what's the positive charges going to want to do? They're going to want to get away from the positive charge and move to the outer edges. It would be just as many as what we've drawn on the inside, so I'm going to complete the circle just to show that it is the same, but the positive charges are purely on the outer surface, the negative charges are purely on the interior surface. And so that's just the first conceptual look. Then how much charge would it be? Well, the amount that the positive charge is going to pull in of negative charge is just going to be that negative Q that we had. Exactly equal and opposite to the positive Q in the middle. What about on the exterior surface? Well, that's going to be, once again, positive Q, right? Producing the same charge as the point charge suspended at the center on the outside of the metal cylinder. So I'll clear my drawings and then we can see this here, that the electric field lines would be drawn from the positive charge at the center to the negative charges on the interior wall of the conductor. Then there's no electric field inside the conductor. It's zero inside. And because they have positive charges on the surface, the conductor then creates electric field lines pointing out. So as I mentioned, the cylinder just looks like, from the outside, a positive Q, which is pretty nifty, a little bit strange, but this highlights some of the ideas of how charges move and how conductors can be extra special and important. We'll take a closer look at conductors in the electric field, as well as even insulators, in our very last section, which is coming up. So let's finish this out.